Hello and welcome to this talk about Aeolian dust sources, transport and deposition of the Chinese Loess Plateau during 1999 to 2019, a study using the FLEXDUST and FLEXPART models. In particular, I'll be examining the linkage between the East Asian winter monsoon strength and deposition of the Chinese Loess Plateau on an interannual scale. This work is done together with my supervisor, Hui Tang, Anu Kakanen and Frode Stordal. My name is Ove and I'm a master student at the University of Oslo. It's estimated that every year more than 800 teragrams of dust is injected into the atmosphere from the arid regions in East Asia, with most of the dust emissions occurring during spring. A significant portion of this dust is deposited over the Chinese Loess Plateau. Chinese loess is the oldest and thickest deposits of Cenozoic Aeolian dust, and during the time frame of millions of years, information about past climate variability has been recorded through the deposition process. The variability in the strength of the East Asian winter monsoon system is thought to be recorded in the loess record through changes in the deposition rate and grain size. The primary driver of the East Asian winter monsoon is the temperature difference between the land and ocean during winter, and it has three major components. At the surface, you have the Siberian high and Aleutian low pressure system. Then at the mid-troposphere, you have the East Asian trough, and at the upper troposphere, you have the East Asian jet. The East Asian winter monsoon also produces strong northwesterlies to the east of the Siberian high. And if we compare spring synoptic situation to the winter synoptic situation, we see that the winter monsoon characteristics are significantly weaker during spring. A previous study linked the Loess deposits and the winter monsoon strength, and in this study they used the cold wave frequency as a proxy for the winter monsoon strength and the dust storm frequency as a proxy for the deposition rate over the Loess Plateau. And as you can see here, there is a strong correlation between the cold wave frequency and dust storm frequency. So based on this, they concluded that the Loess record serves as a valid indicator of the winter monsoon strength. However, dust frequency is not deposition, as the dust frequency index used in this study is based on visibility observations, which is more analogous to concentration, and concentration and deposition would not necessarily be linked during wet deposition events. And that's why we want to re-examine this question and determine whether the winter monsoon strength of the winter monsoon is really linked to the deposition rate, and if particle size might be a better indicator of the winter monsoon strength. To achieve this, we use the Lagrangian particle dispersion model FLEXPART and the dust emission model FLEXDUST, and the transport and deposition processes are handled by FLEXPART, where many computational particles are released from the receptor location and then tracked backwards in time for 5 days, probing for the possible source regions. In our FLEXPART simulation, we carried two particle size spins, 1.5 micron to 2.5 micron and 15 to 20 micron. And the output from FLEXPART is the emission sensitivity, which, when multiplied with the dust emission flux from multiplied with the corresponding dust emission from FLEXDUST, produces the source contribution for the respective receptor location. And when the source contribution is summed up, you get the deposition rate at the receptor location. And all our simulations are forced by ERA 5 reanalysis. The receptor location or included in our study are all major sites of loess and loess deposits, and we also include the SACL observatory to provide future model validation. Our preliminary model validation is based on observational data sets of monthly wet and dry deposition fluxes, originally published by Osud et al. In 2014 in the ACP journal. And we can see that FLEXPART is able to reproduce the spatial variation among the sites, as well as the interannual variation, even though if we compare absolute, FLEXPART is underestimating. However, for our purposes, this is sufficient. To further examine the interannual correlations between deposition and large-scale and local climate instances, we did a major correlation analysis, and the significant values are shown. And as you can see, the emissions from the deserts northwest of the Loess Plateau and Mongolia are all significantly correlated with dry deposition for all the sites. And however, for Taklamakan, we don't see this. We don't see this correlation. And if you look at the wet deposition, the correlation between the emission and deposition is much weaker due to wet deposition mainly happening in single events. If we move on to looking at the circulations, we see that the dust deposition is negatively correlated with the Arctic oscillation and no significant correlations with the winter monsoon indices. So to look into more details in the circulation anomalies creating in strong deposition year, we did a composite analysis where we took the strong deposition year minus the weak deposition year circulation. And here you can see that in the strong deposition year, there is a strong positive mean sea level pressure anomaly over the Arctic, indicating negative Arctic oscillation. And we don't see any large mean sea level pressure anomaly over Siberia, which would be expected in a strong winter monsoon year. The exception being Bauda, which seems to be more affected by the pressure changes over the ocean. And then for the coarser particles, the circulation in strong deposition year are more or less the same as for the fine particles, except for Lingtai and Bauda, which for Lingtai shows more winter monsoon-like mean sea pressure anomalies, whereas Bauda shows more of shows for coastal particle more negative AO mode like circulation anomalies. Then if we look at the source contributions, we see that the western sites like Sakal has a stronger contribution from Taklamakan, and we also see that between the coarse and fine silt, the source contributions look more or less similar. And for both coarse and fine silt, the primary mode of deposition is through wet deposition. Then to further investigate the difference in source regions between the strong and weak deposition year, we see that the strong deposition year has a much more concentrated source contribution, suggesting that you have in strong deposition year you have a large contribution from single dust events. So to conclude, FLEXPART and FLEXDust can reasonably reproduce spatial and interannual variation in dust deposition when compared with observations. The 7 Loess sites show spatial difference in the source contribution. Western western sites have a stronger contribution from Taklamakan. Strong deposition year have a more concentrated source contribution compared to weak deposition year, suggesting a large contribution from single events. The spring dust deposition in all 7 sites correlates well with the winter AO, NAO, but not the winter monsoon indices, and possible mechanism linking the winter AO and dust deposition. Negative AO favors intense cold surges intruding into East Asia, which can be further amplified due to increased snow and cloud cover over central Siberia during negative AO winters. However, further research remains to pinpoint the exact mechanism linking AO to deposition over the Chinese Loess Plateau. Thank you.